Well, all right, students, welcome to the very last chapter, PowerPoints, in this semester. I'm proud of us for making it this far. And so let's finish this thing strong. We are not going to complete this entire chapter because this bleeds over into Chem 2, a lot of this material. It is one of my favorite topics because this marriages it marries so beautifully my love for physics and chemistry together. But it talks about chemistry. Chemistry by definition is the study of the composition of matter, but also the changes that it undergoes. And this talks about energy changes. And see, that's what physics discusses. Physics talks about energy changes. And so if you talk about energy changes while chemical changes are happening, well, then you get that marriage between chemistry and physics. So that's what we're going to talk about in this particular chapter. So we're not going to go very far into it because it can get pretty deep into, and we need to save something for Chem 2. So that's exactly what we're going to do. And then we'll get into Le Chatelier's when you have a reversible reaction. That is very much into Chem 2. So we'll get there next semester if you choose to take Chem 2 in a classroom. So we're going to talk about the different forms of energy and how those energy changes affect chemical reactions, and also the different units of energy, which I will expect you to be able to transform from one to another using dimensional analysis. So please remember what the physics definition of energy is. It is simply the ability to do work or cause change, transfer heat from one thing to another. And in order to do that, we need to think, what is one thing? And we define that as a system. And when you think about what is energy, it's either kinetic, that means it's in motion right now, or it has the potential to be in motion. So it's potential. So it's potential energy that's stored or getting ready to be used, or it is in use right now, so that's kinetic energy. So kinetic energy by definition is that energy that results from motion, and so we have a calculation for that, and it is energy that's from motion right now. So it has this particular formula that involves half the mass. And then this U right here, remember in this particular text she uses a U to mean speed. So half the mass times the speed squared. So you can see that speed is going to be more impactful than the mass is going to be. So things that are moving really, really fast can have a lot more kinetic energy than things that are moving relatively slow, even if they're heavier. Okay, and then one form of energy is thermal energy, and that is the energy content of things like what's going to be more cause you to have a bigger burn, a small cup of water that's boiling, or a very large bowl of water that's at the same temperature. And I would hope that you would know that the large bowl of water that's at the same temperature as that small cup is going to cause you a larger burn. That's because it has more thermal energy. It has more particles. And thermal energy is if you take the amount of energy or the speed of each particle and you add it all up, each of those particles has its own energy, its own heat energy. It has a mass and it has a velocity, and temperature measures the velocity of objects. That's what temperature measures. How fast is each particle going? We've talked about that before. So if you measure each one's kinetic energy, its mass, times its velocity squared, well, you're going to get its kinetic energy. And if you have more particles and then you add all those up, well, now you have all of their thermal energy. And so adding all those together, now their combined energy is their thermal energy. So a small cup is going to have less thermal energy than a large bowl of water. All right. And then you have potential energy. Potential energy is how much energy it has because of its position. So if we have chemical energy, we store our chemical energy in our food, for example, our bodies do. And so energy that has a high content of chemical potential energy, things that are fatty, proteins and things like that, also carbs, carbohydrates, things like that. Okay. Also, there are certain chemical structures that have the ability to store energy well. We also know that we can convert energy from one form to another. We know for a fact that we can take the energy that's stored in our body as food and convert it into chemical energy to allow us to work throughout the day. And we know that chemical energy that's stored in certain medicines can be used later throughout the day because we have time release capsules and things like that for medicine. So we understand that we can use that as well. So we understand that they can be transformed from one to another. Now, we can't create or destroy energy, but we can change it from one form to another. Okay, we're good. That's the law of conservation of energy that says we can change it from one form to another, but the overall total energy has to stay constant. That's the law of conservation of energy. Okay. And we also must identify a system. And that's simple to do, and this is going to become more important as we go on throughout this. A system is whatever we're focusing on. It could be something as small as this little cup right here, or the bowl that we were talking about, or it could be something larger. It could be our Earth. That could be our system, and the surroundings could be the universe. It could be our universe and the galaxy. The system is whatever we are focusing on at that particular time. And then the surroundings is the rest. Okay? So you must carefully define what it is you're going to focus all your attention on and say that is our system, and everything else are the surroundings. That's important for you to stipulate, because it's going to determine. All right. And then heat. Please understand the definition, the true physics definition and chemistry definition of what heat is. Heat is a transferring of energy. It's not how hot or cold something is. Heat is transferring energy between two objects that are at different temperatures. Okay? And it's always, always going to go from the hotter to the colder object. And then thermochemistry is simply the study of heat. That's all it is. All right. You need to know this definition. You need to know the difference between an exothermic and an endothermic. I think of exo as exiting out a building. When you exit out a building, you leave. So an exothermic reaction is a reaction in one in which heat leaves your system. Here's an example. When you take hydrogen and you react it with oxygen to produce water, it also produces energy. So energy leaves the system. So if our system is our cup or our beaker that you're focusing on, then that beaker is going to have its energy to leave that system. Now it's going to maybe heat up for a little while, but then it's going to end up cooler than what it began, because it's going to release energy to the surroundings. And when that occurs, we're going to call our energy negative. Okay? Our change in energy, this is a delta, Greek letter delta, and it stands for change in, and H is heat. So our delta H is going to be negative because we lost heat to the surroundings. And that doesn't mean that we lost heat forever. It means the change in energy to our system was negative, because our system is what we're focusing on, and we lost our energy from our system to the surroundings. Okay? And then endo, think of endo. It's very, very corny. I know it's so corny, I understand. But my granny, she was so country. She was from the very, very, very backwoods of Kentucky. And she used to say, "Come on, endos, come on, it's too hot." And so that's what I think of. I think of her, little old, she was short, oh goodness. But she, "Come on, endos, come on in this house." And that's what I think of. So an endo is come on in. Heat is entering into the system. Like baking a pancake, you have to add heat into or indoors. That is an endothermic process. So when you cook a pancake, you have to add heat into, and it's going to get warmer. So think of that. So your energy is going to be on the reactant side, because you have to add heat to make it happen. You have to add heat to make that happen. All right? So your products are going to end up warmer than they began. You need to know your units for heat. Your SI unit for heat is the joule. That's not joule, it's joule. And it's usually capitalized with a capital J, the unit is, because it was named for James Prescott Joule, who was an Englishman, and he studied energy. So he's an important guy in the grand scheme of things as far as chemistry and physics and horsepowers and things like that goes. So he set a joule, 1 joule is equal to 1 kilogram meter per second squared, the amount of energy required to move 1 kilogram, 1 meter in 1 second, with an acceleration of 1 meter per second squared. So that's what he set it at, 1 joule. There are some other units that you're going to need to know. I will expect you to be able, as I told you earlier already, you need to know, I will for sure expect you to know that 1 calorie is equal to 4.184 joules. This is a big one right here. I want you to know this. 1 calorie is equal to can't say that. 1 calorie is equal to 4.184 joules. You need to know that. And you need to be able to convert. You remember how to do that. If I tell you that something has 6 calories in it, I'm going to expect you to say, okay, my given is 6 little c calories, and I know that 1 calorie is equal to 4.184 joules. So I'm going to cross out my calories, and I can calculate how many joules that is. Okay. Another thing that may be of interest to you is that notice there's a little c calorie and there's a big c calorie. And that is because a nutritional calorie is a big C calorie. Which means if you were to take any food item that you have in the United States and you were to look on the back of it, you're going to see that it has so many big C calories. Now that is a marketing thing as well as a printing thing to save a little bit of money, but mostly it's for marketing. Because if you look on the back of that and you see that a Snicker bar or whatever, peanut butter cracker, whatever you're eating, has 283 calories, let's just say, it's going to say 283 and it's going to have a big C calorie. What you are really seeing is that it has 283,000 little c calories. That's 283,000 little c calories, because those are nutritional calories, or 283,000 283 nutritional calories, or 283 kilocalories. So a big C calorie like this is actually a kilocalorie. And you need to be aware of that. So when you're eating your food, if you ever want to cut back a little bit, remind yourself that's not, 283 calories you're eating in a Snicker bar. It's 283,000 calories, and it might help you cut back a little bit. Okay? You need to be able to switch back and forth from nutritional calories to regular little c calories, and then to joules, because most of the time when I went to London over spring break for my daughter's trip for graduation, they don't do things in calories. They do say joules. That was one of the things I'm nerdy like that, and I really was anxious to see if they did indeed do things in joules, like I had heard, and they do. Their food things say joules. They also now, they have so many American tourists and so forth, that they do have both on a lot of things, but a lot of their food is still says joules. All right, so let's talk about what state functions are and the first law of thermodynamics, and let's get to some math, shall we? A state function is part of physics and chemistry too, but it's part of thermodynamics, which is the very last topic that we'll need to talk about. It's got two parts to it, state functions and calorimetry, which is pretty cool because it tells you how the calories in your food are really found in like food labs and things like that. And you know this already because you did this food lab. A lot of you have already done this food lab, but it's the specific study about heat and other kinds of energy. So there's 3 different kinds of systems that you need to know about, and we've already talked about what a system is. It's what you are actually focusing on. What is it that you're focusing on? Okay, but there's 3 different kinds of systems. There's an open system, there's a closed system, and then there's what's called an isolated system. So let's look at these 3 different kinds of systems. There's a picture here someplace. I wanted to find that. There's a picture in your textbook. I don't remember what page it was, and I don't have my book open with me right now. But let's look at those. I can draw them because I know you want to see my beautiful drawing. Let me draw them for you. An open system, it'd be like a jar that you have. Ooh, let me get a pen. Shucks. Well, I'll go ahead and just write it. An open system would be like a jar that you leave on the cabinet, and it does not have a lid on it. Okay? And so air, things can go in and out. Air and everything can go in and out, flowing freely. That's an open system. Okay? Then you have a closed system. A closed system would be like, let's say you have a Gatorade bottle, and you've got the lid on that Gatorade bottle. Now, you might have Gatorade or maybe a half-drunk Gatorade in there, but the lid is on. That's a closed system. Nothing can get in or out. Whatever's in there is stuck, and nothing else can get in or out. So this is a closed system. And then you have a closed and isolated system. In an isolated system, you might have your Gatorade bottle here that's got the lid on it, but then you've packed it in some sort of insulated container. Now it's isolated. So not only can nothing get in or out, but not even the air. See here, you got air particles that can hit this. So if you put this out in a cold day, this whatever temperature the air is out here is going to be the temperature inside there too. In this case, that's not so in the case of our isolated system. It's insulated against whatever the environment is outside. It's safe and protected. So those are your three different kinds of systems, okay? All right. So in thermo, we're going to talk about how the state of a system changes. We're not so concerned about how it got to be that state in the first place. We only care about changes that happen to that state, okay? And so we're going to talk about something that's going to be important later, especially in Chem 2, and those are called state functions. Things that are determined by the state of the system. And it doesn't matter how it got there. And when we're talking about the state of the system, we're talking about things like what temperature is it at? What pressure is it at? You know, things like that. Those are called state functions, and let's take a look at those right quick. We're going to talk about the first law of thermodynamics, which is super, super important to the rest of this chapter. The first law of thermodynamics says it is totally and completely dependent on the law of conservation of energy, which says we can't create or destroy energy. We can change it from one form to another. You can change potential to kinetic and back, but you cannot create or destroy energy. It says whatever changes there are to a system have to be changed or given to the surroundings. In other words, the total system plus the surroundings has to remain zero. So whatever change to a system has to be given to the surroundings. We can make changes to a system as long as the same change is done to the surroundings. If we lose energy in our system, where does that energy have to go? It has to go to the surroundings. Okay? If our surroundings gives us some energy, it has to be the same amount. If we gain 10 joules of energy, where did all of that 10 joules come from? The surroundings. Okay? The surroundings could not give us 10 joules and it have lost 11 joules. Do you see what I'm saying? It has to be the same. That's the first law of thermodynamics. Whatever change occurs, it has to be equal. And so, if that's true, then we can find those changes. They're always going to be the same. Whatever change there is in a universe, and that U does stand for universe, has to be equal to whatever the final energy was minus the initial. Okay? That's what it's talking about. And they use, Burd here uses a U for the internal energy of a system. Most others that I've seen use a Q, but she uses a U. So, alrighty then. Okay? Keep in mind what energy is. It's the ability to do work or cause change. And so if a system either takes in or gives off heat, then that's going to mean it's going to have some sort of change to its own heat. It's going to either take in heat or it's going to give off heat, so it's either going to get hotter or colder itself. It's going to have its own. All right? So that means that the overall change in our system's internal energy, U, is going to be given by this Q plus W, where heat, Q is its heat and W is its work that it's done. So here's this little formula. All right? So this should make sense to you. Here's sample problem 5.2. Calculate the overall change in internal energy. Remember, that's U, delta U. For a system, if it absorbs 188 joules, so that's going to be positive because we're taking it in. If you're taking it in, it's positive. If you're giving it off, it's negative. Think about that. So it takes in 188 joules of heat, but it does 141 joules of work on the surroundings. So it's taking it in, that's positive, but we're doing some work, that's negative. You take it in, that's positive. If you do work, that's negative. So we take in 188 joules of heat, but we do 141 joules of work on the surroundings. So that would be 188 joules to the good, but a negative 141 because we did that work on the surroundings. So 188 minus 141 is a positive 47 joules. So that is our delta U. That's pretty simple and straightforward, I think. Yeah? All right. And then here's a little table for you that's in your textbook. Please keep this in mind. If you have to add heat to the system, that's an endothermic process, so Q is going to be positive. If you release heat to the surroundings, that means Q is negative. You gave off heat. If you do work on the system, that means somebody else is doing work on you, adding energy to you, then your W is positive. But if you have to do work on the surroundings, then you're giving yourself, so your work is negative. All right. And then here's an example of that. Okay. If you lose heat to the surroundings, then Q is negative. If you do work on the surroundings, work is negative. If the surroundings is doing work on you, that's positive. And if heat is gained from the surroundings to you, that is also positive. That makes sense to you, I hope. All right? And now this is going to be the last couple of things that we're going to be on this video. And then this is if you have the reactions that are carried out. Let's see, yeah. This is when you're going to find out if your work is going to be positive or negative. Okay? Keep this in mind. You got to think of you having a plunger here and a reaction's taking place inside here. Okay? Pressure times volume is right here. This is going to be true. If the volume is going to be constant, so if you have something that your volume can't change, like a closed container, and that can't change. All right? Then here's what's going to be true. Your universe, your internal energy is going to be this situation right here. Your pressure times the change in volume. If your pressure is going to stay constant. All right. Now, I'm not as near as concerned about all of these things right here as I am about the end game. And the end game is right here. That's what I care about, you knowing right here. For any reaction right here. This is what I want you to know. We call the enthalpy, and you need to know this term right here. The change in enthalpy is the difference between the products, the enthalpy of the products, and that means heat. Enthalpy is just heat of the products minus reactants. That's going to tell you how much enthalpy you had to change. Okay? That's all I care that you know. All that other stuff was just leading up to this. Truly it was. It really was. Okay? This is how much heat there is going to be. Truly it is. Alright, now, this right here is going to be necessary for you to know. These little numbers here, they look really hard, and we're going to sit on these for a few minutes. See this number right here? This looks, ugh, but I promise you it's not hard. And I'm going to go to a new video so that I can spend a little bit more time on it. Okay?